Let's get right into the content in this episode, because there's much to cover with rules concerning the limit. I'm going to start with this curve, and as a refresher, here's how functions relate to curves in case you're totally new to the idea and want to start learning calculus cold for some reason. If I take this point where x is 4 and the function is known to be 10 when the input is 4, then I trace it up to where the y point is 10 and I put this point 4, 10 on the plane. If I do this for all values of x, I generate this function here. For most viewers, this is obvious, but I technically never specified this. Moving on, when we need to know the limit at this point on this new curve, say x equals -2, I'm going to color in the curve to the left with the color green and the curve to the right with the color blue. If I can't evaluate the function at the point where x is -2, so I can't just plug -2 into the equation, then these are actually two separate curves with an infinitely small gap between them. So between the green and the blue, there's a really tiny gap where I just can't plug in x equals -2 to get a point there. The limit only makes sense if the green curve and the blue curve meet at that point. Otherwise, we'd have multiple outputs for f of -2. We'd have this green curve and this blue curve, and they wouldn't be meeting, and f of -2 wouldn't make any sense to take a limit. As we approach it, we're not approaching anything, we're approaching two things. If we want to know the limit from the right value, we write it as such. The limit with the positive sign, because it's on the positive side of it. And for the left, we write this as such with the negative sign, because it's coming from the negative side. So, if you're getting two separate values, you can technically look at the limit, what's happening from the left point of view and what's happening from the right point of view. There is, however, one extra scenario for limits that I haven't covered. We can take a limit where x approaches infinity instead of one of those points that are on the number line you could see, like 3 or 4. Look at the graph for 1 over x, for example. You can see as x approaches infinity, then 1 over x approaches 0 as the denominator gets bigger and bigger. 1/10th, then 100th, then 1,000th. This is getting smaller and smaller and smaller. And it's actually approaching 0. For these examples where we have approaching 1 over something and it's going towards infinity, we can actually use substitution to solve the limits. So let's take this new function where f of x equals 3x plus 2 divided by x minus 1 and apply a limit as x approaches infinity. If we substitute in x equals 1 over u, or use just some other variable, nothing special about using that letter, then as u approaches 0 from the positive side, x approaches infinity. As u gets smaller and smaller, the value for x gets bigger and bigger. So when we write f as a function of u instead of a function of x, we simplify to get f of u equals 3 over u plus 2 divided by 1 over u minus 1. We also are now taking the limit as u approaches 0, and that does the same trick to make x reach infinity, as we recalled before. Now if we multiply by u divided by u, which is the same as multiplying by 1, which does nothing, we get the expression f of u equals 3 plus 2u divided by 1 minus u. Now we can use our limit to substitute in u for 0 because there is no division by 0 anymore to reveal that the limit is 3. Pretty cool, right? You can use substitution when solving limits as long as you can change what the variable approaches according to how your new variable relates to your old variable. If I said x equals 3u and it was the limit as x approached 9, then we could see that u approaching 3 does the exact same task as to get x up to 9. We also have two ideas with taking apart limits. The limit of a sum is the sum of its limit, and the limit of a product is the product of its limits, as long as the individual limits can be evaluated. For example, for the sum rule of limits, let's take x plus 1 divided by x as x approaches infinity. We could break this up into x over x plus 1 over x, and then simplify into 1 plus 1 over x. When we take the limit as 1 approaches infinity, it stays as 1. And we take the limit as 1 over x approaches infinity, we get 0. And for products, we could best see this for the function 5x approaching 3. These two limits are approaching 5 and 3 respectively, and this leads to the total limit of 15. We cannot break down x over x approaching 0, which would be 1, as the limit on the top approaches 0, but the limit on the bottom can't be valued. So we can't break up a limit if its two parts have a limit that can't be evaluated. So both separate limits have to be evaluable in order for you to use this. And we can see that subtraction follows from the addition rule, and that division follows from multiplication. As one last rule for limits, at least until we have the ability to find slope, is the squeeze theorem. Look at these three curves. The top curve is always the greatest. The middle curve is always the middle, and the bottom curve is always the bottom. If these curves are called f of x, g of x, and h of x, we can write this result as h of x is less than g of x is less than f of x. Notice how there is one point where the functions f, g, and h seem to meet at the same location. And this is where the squeeze theorem comes in handy. To find the limit of g of x at this point, we can find the limits of f of x and h of x and see how g is squeezed right between them. If the limits leave us with a scenario where our original inequality becomes evaluated to something like 1 is less than the limit as x approaches 0 of g of x is less than 1, then the limit must be 1, because the number between 1 and 1 is obviously 1. If all those techniques I mentioned before fail, then plugging in numbers closer and closer to the limit on your calculator can actually yield a numerical approximation. If the numbers seem to be getting large quickly for a function approaching infinity, then it likely won't limit to anything, and it's just going to go off to either positive or negative infinity. And if the limits on the left and the right ends don't seem to be meeting up when you try using your calculator, it also probably doesn't have a limit. Now, that's enough to cover for today. In the next video, we start learning the most useful tool in basic calculus, the derivative. And as always, keep on learning.